Watch This is really fun. I don't know who wrote this into Desmos, but it's really a fun thing. Isn't that fun? I don't know what behind the scenes maybe. Ooh, how fun is that? Such a nerd. Okay, this morning I saw these equations for this, and now I can't find the equation, and I don't think I have a behind the scenes, but maybe I do. Oh, there we go. All right, so those will make the letters love.
Whoa.
Isn't that fun?
I feel like that one's easy. That one,
Yeah, I feel like, yeah, we could do that. Okay, there's also polar graphs that make hearts, but I need to move on. All right, so that was fun. All right, this is probably maybe going to be a bit aggravating to write on, so I'll just do some, I can't not do Valentine's Day slides though, hang on. Insert picture from, oops, cancel. Where's my gallery? Here we go. We'll use this one. When I found out I was going to move to New York, I had a few weeks left in Memphis. It was like sudden. I moved between October and November, and I quit taking people's pictures for my slides and just told them I was going to put hearts on every slide every day that I was still there. So that reminds me of them. I did. I left November 22nd.
So who taught calculus?
It didn't work out very well. They hired a guy named Josh something. I was sat in on the interview. I pretty much just taught him remotely. So anyway, what we're talking about right now are cross sections before we start Solids of Revolution. I just wanted to go in and get all the illustrations and the food and the, paper things out. Okay, girls, look now. Sticking out of this base, like if you have a base of a certain shape, it all depends on what's sticking out of it as to what it'll make. If there's triangles sticking out of it, it'll make one thing, okay? If there's squares sticking out of it, it'll make another thing. It'd be really cool if I was able to bring up squares that as I move them would get bigger and larger as I go. But I showed you the illustrations on my topics page that allow us to do that. Didn't I? The other day?
Yes.
Okay. Let's look at that again. I think it's good to. Okay, so there's a lot of good information. Yeah, it was Newman when I moved here. Has the internet been slow?
Yeah. This whole week.
All right, let's do number 3 so that I'm not wasting any more time. All right, so I did 1 and 2. If you didn't watch the video, you may want to do that. So, and I don't even know if I have one for me. There it is. Those are the answers. Cross section. All right, on cross sections, we're not revolving anything. Nothing is revolving if you're doing something by cross sections. And they'll say it. They'll say by cross sections. It actually usually comes later in the book, and most teachers, I've taught it some years after Solids of Revolution, then it's so hard for me to get kids to realize you're not revolving once you learn revolving. So I do it first because it doesn't matter because they're different. And a solid of revolution, in a cross section, the object is already made, and I'm just going to turn it and start slicing it, and like you heard on the video, just see what's falling off on the cutting board. It's already made. I'm not creating it. Okay? So you have an object that you're just going to start cutting, and you imagine me standing over it with my cutting board doing this. And y'all saw Hershey's Kisses triangles, Toblerone triangles with all of them. Just like cupcakes that make circles. I was cutting it. Caitlin brought cupcakes that were already made. She didn't bring in something that I revolved around and made a cupcake, okay? Now, what the difference is the different shapes that we desire to make, and so you make decisions depending on that. So the object's already made, and then we're just gonna slice it. And surprising things can happen. I've cut one of these before, we talked about the other day. I think if I slice this really thin, it'll make a trapezoid. Each slice will be a bigger and smaller trapezoid coming toward me. If it was perfectly cylindrical, then each slice would actually be a rectangle. If you take a can and you slice it, and then you slice right next to it, you just have a rectangle, especially if it's a solid, okay? All right, so let me see if my website's up yet. Okay, no, wow, that's not fun. Okay, apparently wanted me to refresh. Okay, so under topics, let's see. It's kind of bad that I put cross sections under volumes of solid. Well, no, that's okay, because I called it volumes of solids. I didn't say how I was doing it. So these are cross sections. And I think I showed you this the other day, and it's way better and once you see all the cutesy stuff, it's really good to look at. So we're gonna just first talk about objects that are already made, and I'm just gonna be slicing them, hopefully. Please. Maybe my computer, that shouldn't be that. Okay. So if I do an equilateral triangle, the cross section, so I'm cutting it, and so all I'm doing is looking over it, and y'all see it has a circular base. And if I have equilateral triangles, then
You have to drop the axis.
there's poking up out of it. They're going to grow based on my equation. My equation's going to contain them. And I can add up equilateral triangles, okay? And it would make this picture, which I would have a hard time imagining. Really cool with like kind of an edge to it. So it's this solid, and that triangle is growing within it. All right, now if we did the chords again, and we've got a different kind of triangle. I think these are right triangles, okay? It makes another figure. And so we're adding up the triangles with our magic integral symbol. And it makes a little bit of a different super cool solid. It's amazing the curvature it can have as you go slowly, but you know that from tangent lines, right? They create a nice curvy thing. All right, so here's one with semicircles. You did all of this kind of for homework. And so, oh, by the way, we have new equations. Do you see there are equations that are determining all the different dimensions that we need? And so nothing to prevent you from adding up semicircles from A to B. Okay, so these solids are already made, and I'm just slicing them. And down here, you get the wonderful, I hope I drew a little smiley face if you watch the video. Like, these are easy. Do not mess these up, okay? They're really easy. You may have struggled with number 3, and I'm going to do that one in just a minute. But it's really, really, really nice to see this.
When you wrote super easy, I wrote it on my paper too.
With the S's?
I thought it was cute.
Okay, so they're super easy. Don't make it difficult, okay? Because it's just like you're sitting in geometry and you write the formula for an equilateral triangle, and then you make them grow from small to large. Let's do number 3. All right, on number 3, we had, and Celine, I think, was the one that came by this morning. A couple of y'all came by, but she noticed that I didn't read it correctly. I started working it like this. First of all, you want to know what all your boundaries are. Like, what's going to make the base of your object? Is the base of your object going to be circular? Is the base of your object going to be rectangular? You know, whatever the base of yours is going to be. whatever interesting figure you want it to be. Alright, so we have y equals x cubed, and y equals 0, which is the x-axis, and right now it's not contained, it's open-ended, but if we throw in x equals 1, then it's contained. These intersect, x cubed intersects 1 at 1, 1. So that's 1, 1, this is 0, and this is 1. Okay? And I grabbed it, I'm like, oh, okay, so I'm cutting it this way. And then we looked at the answers and I go, like, anything like that. And it wasn't even what she was asking me, because you may have been surprised at the answers too, all right? Because this one all of a sudden said, find the volume of the solid for each of the following cross sections taken perpendicular to the y-axis. So the person with the cutting board is not cutting it perpendicular to the x-axis right now, they're cutting it perpendicular to the y-axis with their knife. So they're standing over it. All you could see is the base right now. You don't know what's poking up out of it, okay? But something is, it's already made. All right, so I've got to make my slices perpendicular to the y-axis, and whenever I go across, I'm doing an x, which is an f of y. Train yourself to react that way. If you need to write this down, horizontal ones are x's, which are f of y's, they're functions with a y in them. Verticals are old stuff, they're y's, and they're in terms of x. You go across the x-axis to find the up vertical distance. You go up the y-axis to find a horizontal distance. Watch this if I fill in an xy chart to y equals x cubed. In fact, I'm going to solve it for x. X is equal to the cube root of y, which all agree now I have an f of y. And I'm doing that because it's perpendicular to the x-axis. And those things are x's. All right, so if I fill in for y, if I fill in 8, the cube root of 8 is 2. So when y was 8, x was 2. When y is 1, the cube root of 1 is 1. So when y was 1, x was 1. Do you see how I'm filling in my y's and it's finding the x's? Happy Valentine's Day. Was that just like spur of the moment? Was that just?
I wanted to land her to sleep, but then I just hugged her instead.
Okay, so anyway, when I'm climbing up the y-axis, I'm finding x's, okay? But I need that purple distance, okay? So you can do right minus left. Do you see that this blue distance is all the way across at 1? And if I want the purple one, I have to say blue minus red to actually get this figure right here that I'm trying to get with these, whatever they are, poking up out of it. I'll have different things poking up out. Any questions so far? All right, so here's how I react. So I'm gonna stop over explaining it. I'm just gonna do it. So this is how I react when I see this. I go perpendicular to the y-axis, I underline that, and I start to do sideways rectangle for me to look at. And I'm going to take the integral for cross sections. They're super easy. You're just going to do the area of whatever you have, dy. Make sure you know what your y's go from 0 to 1, okay? All right, now I'm going sideways, so I need this distance. The way to get this distance is to say this minus this. And so my x's are 3 are the cube root of y, and I want to subtract those off. And so I said 1 minus the cube root of y is the length of this part going across the base. And then I got to look and see what it is I'm making. On the A part, I'm making squares, and so it would be that square. You shouldn't, they were all decimal answers, so you may have thrown them in your calculator. A lot of times you shouldn't throw them in your calculator because then you and I mess up on the algebra and the arithmetic, and you can't let that go. I can. What's going to happen the rest of the semester is you're almost always going to just want me to get it set up for you. But in homework, you better not stop with the setup or something will happen to your expertise. You need to do all that drill just like in basketball or golf or fencing or music or, you know, when I hear the Marymount Singers, I think they always start with scales. And you can stand there and go, I know how to do that, but you're going to lose it if you don't do it, okay? So make sure you finish the problem when it's appropriate. Okay, so that was A. All right, on the B part, we have semicircles. Now everybody listen carefully. this is what I see messed up the most, and I usually put this on the upcoming test, which by the way is February 26th. I changed it because Sophia and Caitlin ended up with 3 things on the same day. It was the only reason I changed it. We have mass that day, so just trust me to manage that accordingly, okay? Alright, so now there's semicircles popping up, and you just gotta add up semicircles. Semicircles are pi over 2, integral from 0 to 1 of the radius squared. This is where people mess up the most. Girls, watch. This green is not the radius of that semicircle. This green is the what of that semicircle? Diameter. So I'm gonna have 1 minus the cube root of y over 2. Don't forget that. Because as I go across at the diameter of the semicircle, I need the radius. Are y'all okay with that? Okay. And then equilateral triangles. When you're doing an equilateral triangle, please go straight to square root of 3 over 4 side squared. If you memorize that, you are allowed to go straight to that with an equilateral triangle, okay? And so you have 0 to 1, and we already knew the sides were 1 minus the cube root of y squared dy. Any questions? And the semi-ellipse was maybe a little confusing because you may not have known what A and B were because you've probably never taken the area of an ellipse before. So the area of an ellipse they gave you back up earlier was the area is pi is equal to area is equal to pi AB, where this is A and this is B, or vice versa, okay? And so you have to be really careful with the wording here. So I'm gonna say pi integral from 0 to 1, pi over 2 because it's a semi-ellipse, and I'm gonna have A times B dy. Alright, the base of it is this thing I keep finding, 1 minus the cube root of y. Oh, I'm sorry, that's not A. A is half of that. A is half of the, like, major or minor axis, okay? So it's half of that. The wording was kind of weird though, and it said the heights are twice the length of the base, and some people were confused. Did they mean twice this? Or did they mean twice this? And they meant twice the length of the actual base. And so I doubled 1 minus the cube root of y to continue on. And I think that was the answer. Okay? Alright, any questions about cross sections? Alright, Anna?
Can we go over the, like, I think it was an isosceles triangle.
Alright, so number 2? Or any of the isosceles triangles?
Part 2D, like,
Okay. Girls, you've got to really read it and not make the mistake I did. You've got to see where the base of the isosceles triangle is resting. They could do it with the hypotenuse, where you pick it up and put the hypotenuse, like, I wish I had a right triangle, I don't. There were some upstairs, I think. But if this was a right triangle and this was the hypotenuse could be resting in the base, or one of the legs could be resting in the base. You don't really see a difference because this is an equilateral triangle, but hopefully you can see what I mean because I can't draw. Alright, so I've got to make sure I know where the hypotenuse is. So if this is x and this is x, the area of an isosceles triangle is 1/2, I was going to say x squared or side squared or whatever you're going to say, but I got to be careful here because the hypotenuse is in the base of the solid and we're going perpendicular to the x-axis. We have x squared plus y squared equals 4. I'm glad you asked for this one. I probably did it on the video similar to this. And we're going across like this, and you maybe did A, B, and C. Now we have an isosceles triangle with the hypotenuse is in the base of the solid. So I have this like right angle right here, okay? And so if you want to add up the area of an isosceles right triangle, you're going to have to say 1/2 sine squared dx, and watch this, girls. I made my x's go from 0 to 2 probably in the video and double. Do y'all see that whatever happens over here is symmetric with whatever happens over here? Did I do that in the video?
yeah.
Okay. And did they do that in the answer sheet?
No.
Alright, I'm just gonna go from -2 to 2 so it'll match the answer sheet. Alright, so let's go off to the side and do some geometry. And so, how am I gonna find the area, which is Anna's question probably, how do you find the area, if you know the hypotenuse? How do you go backwards to find the sides? What if you have, isn't this A root 2? So to go backwards to get a side, what do I divide by? Divide by root 2. Okay, so whatever you've already decided is your base, which I wanna make sure I'm giving it as an answer choice. So, let's talk about this. We have x squared plus y squared equals 4 that is dictating how things grow and shrink as it goes up and down. I'm sorry. These are perpendicular to the y-axis. So as they go up and down this way, as I make my slices perpendicular to the x-axis, I'm going like this. So I drew it wrong. So I'm going like this, and I have a right triangle poking up out of all of these. Okay? So if I'm doing it perpendicular to the x-axis, I want to solve for y. Y squared is 4 minus x squared. You do need to think about y as plus or minus the square root of 4 minus x squared. Okay? This whole distance right here, look girls, this is y and this is y, so the entire distance is 2y. Okay? So this entire distance is 2y. Now, let me see how I would do that. I'm trying to think how I would explain it. I guess what I would say is I haven't really addressed this yet before, so let me think how I'm gonna say it. When I'm real aware that I'm gonna be doing side squared, I'll probably never get to the square root part. Because I'm just gonna turn right around and square it again. Did you see what I mean? So I knew right here, I was gonna have some sort of 4 minus x squared in it. But you gotta be real aware of what y is and what's happening with your hypotenuse. And so what's happening is your hypotenuse is this way. I'm sorry, I drew it wrong a little while ago. It's perpendicular to the x-axis, so this is my hypotenuse. So my hypotenuse is 2y. And what are the sides? Are 2y divided by root 2. Are y'all with me there? And then I'm gonna square them. So this is gonna give me 4y squared over 2, or 2y squared. Now let's stop and see what I have here. Alright, so this is the hypotenuse, and it's created by 2y, not just y. Then to go to one of the sides, I divided by the square root of 2 so I could get the sides using my geometry. And then I said side squared, and I got this, so this is my answer right here. I have 2, and then I have y squared, which is 4 minus x squared. And these 2's cancel. And I think that was what they had. Yeah. And I kind of stumbled through that because I drew my line the wrong way again, like I did with Celine this morning. You gotta be really careful. I should say I did it on purpose to make you think, but I didn't, because I just come from number 3. On number 2, I should have made it perpendicular to the x-axis. Girls, before we move on, do you see the things that you've got to think about? But certainly your calculus teacher should expect you to know what 45-45 ratios for your geometry. And you go from the hypotenuse to the side. And it's so much easier if one of the sides is in the base, because then you don't have to deal with that. You just go 1/2 side squared. So what you've got to think about is what's going on with your figure, as if you have like something like this, and the slices were perpendicular, and you've got semicircles, you've got to be real aware that that's the diameter. And by the way, I would go top minus bottom to find all of my y values, and use them in whatever area that I have, okay? And so then if it's the hypotenuse, I have to go backwards and find the side. And it doesn't happen a whole lot, but it, always do it when you kind of struggle with it. That's a great question. Thanks for asking. Anything else on cross sections? All right. So let's look at watch the time because I have handouts. Let's look at some more animations, because these 2 days you can see are really heavy on visualization, and then we're just going to quit that and just start cranking things out, okay? So volumes by disk and the x-axis.
Over here, I've drawn part of the graph of
Sorry.
y is equal to x squared. And what we're going to do is use our powers of definite integrals.
I'm not gonna, it's not only 9 minutes long. A lot of y'all like Khan Academy, girls. I don't link to anything on my site that I don't totally approve and like teach the same way, so it's not confusing to you. That keeps you from finding things that are confusing to you, I hope. But
If I do it from the top, it would
he
look.
can draw a lot better than I can.
Let's
He really tries. It's nice.
Oh, sorry.
0, and we have an infinite number of them. That's the whole power of the definite integral. And so you can imagine as these dx's get smaller and smaller and smaller, these rectangles get narrower and narrower and narrower, and we have more of them, we're getting a better and better approximation of the area under the curve until at the limit we are getting the area under the curve. Now we're going to apply that same idea, not to find the area under this curve, but to find the volume if we were to rotate this curve around the x-axis. So this is going to stretch our powers of visualization here. So let's think about what happens when we rotate this thing around the x-axis. So let's for you to rotate it, and I'll look at it, say we're looking at a little bit from the right. So we get kind of a base that looks something like this. So this is my best attempt to draw it. So you have a base that looks something like that, and then the rest of the function, it looks kind of like, if we just think about it between 0 and 2, it looks like one of those pieces from, I don't know if you ever played the game Sorry, or it looks like a little bit of a kind of a
A
weird
chocolate
hat.
kiss.
So it looks like this, and then we shade it in a little bit.
Okay,
Shade it
so those you can view. I mean, those are both good links, but this, if I can pull it up, hopefully it'll give me this little trial. I may not can open it because I guess my computer doesn't. Okay. Okay, so watch this. I didn't want to do that. I don't know how to undo it.
I love doing that. I love that bookshelf, and it was so stupid.
Okay.
And that was, have you seen my bookshelf too? It's like, I don't know why I'm asking you if you've seen my bookshelf. It's like really tall. It's like different. But what if you can't reach the top shelf? Is it? I can, because I'm good like that.
Okay.
No, you put it together when it's
So girls, quiet.
No, just reach up.
Girls, this blue rectangle is an f of y, and it's going around the y-axis. Okay? That's what we call a washer. What I was trying to do first was make it flush up against the axis it's revolving around. And by the way, it's not going around, stay listening to me. By the way, it's not going around the y-axis, it's going around a line that's like the y-axis that we need to learn how to do that in just a little while, or later next week. All right, so we're not going to do shells together. I'll send you a video, and I want you to learn shells, but shells make this.
It's
okay?
like dizzy bats shells.
Shells is like dizzy bats, yes.
Yeah.
Okay. All right, so these are great. All right, watch. If it does it. Okay, so they're dividing it up into top minus bottom. Those are f of x's. And then they're going to revolve around the x-axis. So they're just going to take a rectangle for you, like I did with my silly styrofoam stuff or my fold-outs, my paper things. And it's going to revolve around and go, quote, and literally full circle. And then you would add up each one of them using the magic integral symbol. And then what in the world it would make, I really can't even envision. Okay. Some of them they give you a picture of, but this is pretty cool. Oh, so here it is, same object. And so they're taking just teeny tiny slices and revolving it around the x-axis to make, this is what it would make.
Oh, it's like a volcano.
Yeah. It's like a tree trunk hollowed out. Yeah, like a little cone.
A lampshade. There we
Or
go.
like a lampshade.
I'm so smart.
That you
Oh my
are.
god.
Okay, so let me do an example real quickly before we go. And then I also have some handouts for you. But you can look at any of many or little as those at your leisure, okay? But I wanted to make sure you knew that it was there. So I'm gonna do this one. All right, so listen carefully so I can squeeze this in because I want to make sure I do. I might even get 2 examples done. All right, we're finding the volume of the solid formed by revolving the region bounded by the graph of f of x equals the square root of sine x and the x-axis. And like I found out with Celine and then with myself just a second ago, I need to see what's going around. It's going around the x-axis. All right, so everybody, if you're tempted to talk, keep your mouth shut and listen, okay? I'm sorry, that sounded super rude. I didn't mean it rude, but I mean, it's a great example. It's going around the x-axis. That's important. If you're going around the x-axis until I tell you otherwise, you want to do it f of x. If you're going on the y-axis, you want to do f of y. That'll create disk. X-axis, f of x's, okay? All right, so if you don't have a calculator, you know the square root of 0 is 0. And I think they gave me limits of integration. They said 0 to pi. Sine of pi is back to 0, and the square root of sine to pi looks sort of like sine does. Because the square root of 1 is 1, so it doesn't change a whole lot. And it just needs sort of a pretty good picture of it. It's contained by the blue graph. That's coming, well, it's the square root, so there wouldn't be any negative parts, right? And the x-axis. And so first of all, it's contained, and then I'm going to make my slices that are going to revolve around the axis and make like a football, I think.
Yeah.
Okay? And so each one of these little things are disks, which are pi r squared h. What I mean by h is you see the width of these disks are going to be whatever you're changing by dx. It's going to be infinitely small, but it won't be 0 or else we wouldn't have anything. But dx is, I'm moving across, y'all see what I mean? I'm moving across the x-axis. And so these have a volume. But it's almost basically just pi r squared, isn't it? Okay? So if you had circular Pringles, it would be hard to find the volume of it. Because we'd go pi r squared, but it'd be really hard to find h, wouldn't it? Do y'all see what I mean? They're barely 3-dimensional. But they do have a 3rd dimension. And so our dx is what's getting infinitely thin. Ask a question if you have it. Okay. All right, so do y'all see I have pi r squared h? All right, so I'm taking the volume of just one disk, like a penny. You know, that has like a little bit of an edge to it. So I'm taking the volume of a penny. Hey girls, if we had the volume of a penny or a dime, we'd go pi r squared times h. And this is our h. So the radius is created by top minus bottom. So this is square root of sine x minus 0. And I'm going from 0 to pi, and then you could work it out. It's not too hard, okay? But like I said, you'd want the setup. Now, time out. I mean, don't go anywhere. Find the volume of the solid. If we, I tell you what, I'll stop there and tell you what I want to do with the hand.